So couldn't you also just use the so what we have been doing this last summer? Couldn't you just use those equations and then just graph?
Yeah, you could do that if you wanted to, but you'll find that some of the problems that we'll encounter will be more easily handled by the graphical technique than by writing all the equations and then plotting them.
Okay.
The other thing you'll find out too from these graphs is that you identify maximum values really easily. So there's an advantage to this technique. So let's look at these problems. Starting with this one, simple cantilever with a load P, length L. I'm going to kind of shortcut this a little bit, and I figure at this point, you guys will probably already know or can figure out that the reaction is P and that the moment is PL. So we'll just go right to the shear force and bending moment stuff. So starting here at the shear diagram, what is the shear at the left edge? Is this kind of force up? Is that positive or negative shear? That's positive, right? So that means I'm going to start at P. Now this is a little weird out here how I'm going to end, so let's just not worry about it right now. I could show you how to do that. In fact, if you were to cut the beam really, really small at the end and look at that little chunk with the load P applied here, and then we'll go internally and we'll assume we have a positive shear force. Okay? If you look at the equilibrium of this chunk, what's the shear going to be equal to? Positive P, right? So that means we're going to have a positive shear force out on the end too. So we kind of know where we're going to start and we know where we're going to end. Now our basic equation says that the change in shear is the area under the load curve. So looking at the load curve from left to right, what is the load? Nothing. 0. So if I start at P and the change is 0, I should end at P. And I do. We also know that the slope of the shear diagram is equal to the load. And what's the load from left to right? 0. So that means that the shape of my curve connecting these 2 points should be a slope of 0. So there's my shear diagram, constant P. That's a pretty easy one, right?
But not on the exam.
This is not going to be on the exam, no. All right, so now let's look up here for the moment diagram. What is the bending moment at the beginning point? Bending moment. We know the value is PL. Is that positive or negative?
Negative.
It's negative. So we're going to start at negative PL. What's the moment at the free end? 0. So according to our relationships, we know the change in moment is the area under the shear diagram. So what is the area under our shear diagram? Looks like it's positive P times L. So if I start at negative P and I add PL, what do I get? 0. So that works. And the moment, the slope of my moment diagram is equal to the shear. What's the shear value? Constant, positive, and equal to P. So here's a constant positive slope, which just happens to have a slope of P. So there's my moment diagram. So without writing an equation, where's the maximum moment in the structure?
At 0.
At the connection, and what's its value?
PL.
Minus PL. Where's the maximum shear occur? Everywhere. It's the same value everywhere, right? All right, let's work on this one. So what is the reaction? If I sum forces in the x direction, what should my reaction be? I don't have one. 0. But I do have a moment reaction. It looks like that. So using the same ideas we had before, so I start off with 0 shear, and I end with 0 shear. The change in shear is the area in the load curve. Area in the load curve is 0, so that works. And of course the slope is equal to the load, which is 0. So this is a really hard diagram to draw. Basically there is no shear. Can't really see that too well. I'll draw it a little bit differently just so the color might show up. Now starting with the moment, what's the moment on the left side? What kind of bending moment is that? Positive or negative? Positive. What kind of bending moment is that? Positive. So again, we know we're starting, we know we're going to end. According to this, the change in the moment is the area of the shear diagram. What's the area of the shear diagram? 0. So m naught plus the change is m naught. The slope of the moment diagram is the shear. What's the value of the shear everywhere? 0. So everywhere I have 0 slope. So you get constant moment. So where's the moment maximum? They're everywhere. And what's its value? M naught.
There's no shear.
There is no shear. 0 shear. Okay, those are pretty easy, so I'll stop here and we'll get some that are a little more challenging.